Thank you everyone for coming to this session here today. My name is Sheree Millet. I'm with L3 Harris Geospatial. I'm based in the US and I've been having a wonderful time being here for almost the entire month of November, attending the different Esris. So thank you very much for Esri Australia for hosting these events and having me here. Today we're going to talk to you about how we can use SAR data to monitor critical infrastructure stability. Specifically what we're going to be looking at here today is a case of tailings dams. Now here in this particular example that we're going to be talking about, there are roughly 3,500 tailings dams worldwide and over 300 collapse each year. This particular one that we'll be looking at here today, so in this particular example here, what we're focusing on is this particular region in Brazil. Now in this particular area, this is where the large Brumadinho dam had a very catastrophic failure in January of 2019. Now in this particular dam, this was certified as actually being stable prior to the collapse. Now this is something that is very important as we consider how we can look at this and see how can we use some of the different technologies that are available to us to actually understand how we can look at monitoring this type of critical infrastructure. Now here in this particular case, this is what the dam looked like on the left prior to the dam collapse, and you'll become familiar with this interface. Now, the top of the dam is where the compaction is for the tailings there, and then the lower portion is the front face of the dam there. And you can see after the collapse what that looks like on the right-hand side. That's where the mud flow occurred. That's after the dam failure occurred at the front of the dam, and all of that mud flow was released outside of that particular dam location. This traveled many, many kilometers downriver, about 300 kilometers downriver is where this particular flow occurred. Now, when we start looking at some of those particular areas as well, this disaster occurred in Dam 1, which is that tailings dam in that particular location in Brazil. And when this disaster did occur, there was 12 million cubic meters of tailings that were released out of that particular dam. You can think about the catastrophic events that occurred around this and all that toxic material running downstream from this particular location. So when we start looking at that, you can think about that much material heading down from that river. This particular incident at the dam was Brazil's deadliest mining disaster. Many workers were still unaccounted for at the time, and at that time of the disaster, 300 were feared dead. Would it have been possible to detect any of these early signs of instability using synthetic aperture radar or SAR data for this particular type of analysis? Again, on the right, you can see the particular location now of the dam and the extent of where that flowed all throughout the entire country. When this particular area had the disaster, not only did 12 million cubic meters of tailings get exposed downriver, over 300 kilometers of the river were also exposed to this, but it also went through 4 different states in Brazil, and actually all that material went through 2 different hydroelectric dams as well. So the extent of the devastation across this area was very, very dramatic. We can see here some different images of what that looked like now as we start looking at some of the before images of what the dam looked like. In the top was the portion of the upper part of the dam. In the middle there is where the dam structure failure happened. Here are some graphics after what that looked like now when the mud flow started occurring and expanding outside of that particular area. Here's another image to show you what that looked like before and after. And then again, here's where that mud flow started flowing outside of that particular catastrophic failure. So you can see now the extent of where that's occurring, not only through the upper portion of the dam, but starting to go through the different agricultural fields as well. So all of that material was flowing downriver, getting it across all those different areas. So we want to know is, could we have detected some of this failure? Could we have detected some of the early signs of this movement and seen what we could have done to look at this differently? Now here in this particular portion, we have a lot of coverage with different types of satellite data. We wanted to use different types of data to do this type of analysis. We can't be there on the ground to monitor all the time what's happening. But can we look at using remotely sensed data, such as SAR data, to look at this? So we used freely available Sentinel data. Now this resolution was sufficient for looking at a large scale type of disaster like this. You can see that it's a 15 meter by 15 meter pixel spatial resolution. So that's plenty of room for us to be able to look at a large scale type of analysis. And we're looking at the range of data here, and the coverage is very sufficient. We wanted to understand, looking back over time from 2015 through 2019, again remember the collapse occurred in January of 2019, So we have access to data all the way up into right before that collapse occurs. And with a revisit time of 6 days in this particular type of data, we have plenty of data to be able to go ahead and start putting together that historical record of what does those changes look like over time. Now, one of the important things to note about why we want to use SAR data is SAR data can be captured day or night, and we can image through clouds. That means we can rely on the fact that any time of day when we need to actually get some data or worry about an acquisition, that's fine, we can do that. We're not reliant on a clear, cloud-free day to be able to have access to imagery. We can go ahead and do that at any time. We can image through clouds. This is important in this part of the world as well. In Brazil, with the tropics and so much of the cloud cover over the Amazon, that we don't have access there to freely available cloud-free scenes optical data. So using SAR data is very important. Anywhere else where there's a lot of cloud cover as well. That way we don't have to worry about that and we can image through clouds. Now this is what we call an active sensor. That's why we can do this through day or night and through clouds. The signal is being emitted from the sensor and it's being reflected off of the ground, very simply put, and being measured back again at the sensor. When it does that, we can do a measurement of the different signals, and that way we can start understanding what's happening on the ground. Very simply put, if an object is moving toward the sensor, we're going to observe that as a positive displacement. Something is rising up toward the sensor, some sort of uplift, upward movement. Contrasting that, if the object is moving away from the sensor, we're going to observe a negative displacement. So if there's a landslide or some earth moving down or a building is moving down, for example, we'll be able to measure that difference in that positive and negative so we can actually start looking at measurements on the ground and understand what's happening. So just as a visual reference also, looking at an optical sensor and a SAR sensor is very different. Here's looking at an optical sensor because now we're looking at the wavelengths, looking at the true colors and so forth that we see with our eye, the type of sensor like that. But when we're looking at a SAR sensor, we're looking at different types of returns that are coming back to the sensor, different types of energy levels, different types of polarizations. We need to interpret this differently to understand what's happening on the ground. So to do this, we use the software NVStarscape. This is the software package that we have to be able to do the full analysis of working with SAR data, to be able to bring that in and do the different types of analysis we need to do to understand these types of measurements and changes over time. We looked at a wide variety of the satellite data. This is using the Sentinel data reader, so we can bring all the different data sets in. And then if you look in the area focusing on the box there, you can see that this is the area in the portion of Brazil and the dam that we're going to focus on to be able to look at the different data that we have there. You can also look at the color bar showing the amount of change over time. We'll be referring to this through the next series of slides when we start understanding what type of movement we're looking at here. So here's a velocity map looking at some of the mean velocity of the movement. And here again, we're looking at millimeters per year. If you look at that color bar on the far left, that's about 25 millimeters per year in the the purple and blue regions there. So now as we start looking at that dam movement, you can start understanding this is the type of scale that we can measure and the type of scale where you can start seeing the effects of that type of movement and collapse. Here's another graphic showing, again, the velocity over the particular dam location. Now, let me give you a visual of what this area looks like, because it's hard to look at just satellite imagery or SAR data and get an understanding of what type of impact this occurred when this dam actually collapsed. So here's the graphic of what this looks like. There are many videos and many images that were taken at the time of this disaster, so it's well documented what this looks like. Again, you'll start becoming familiar with the view here. The top is where that compaction is occurring at the top of the tailings dam, and the front area is going to be the front of the dam that you'll see in many different graphics. Here's where the collapse actually starts in this particular location here. And what we have also is many videos that were posted at the time of the collapse. So if you start looking here in the video, you can see at the front part where the wall is collapsing there, and then as that entire landmass starts sliding, you can see the back portion of the video here where the back wall is starting to occur and all that impact is happening. You can see now that there are many buildings and structures related to the dam and all the locations that were needed for that, and those all start getting impacted straight away by the flow of dirt from that collapse. This is just one of the views that we had from the different videos that were taken. Here's another view looking across a bridge over one of the construction areas. You can start seeing now the impact of the mudslide that's occurring further upstream from the dam collapse as that starts moving toward this particular bridge. Here's the mudslide that's coming in from the left. You see for scale, there's some vehicles on the right side of the image as well. They're trying to understand what's happening and that all of a sudden they need to get out of the way. So here's just having a graphic of this massive mudslide that's coming through. Again, this went on for 300 kilometers downriver from the tailings collapse. 12 million cubic meters of tailings that went through this. And that's just what was able to be measured. Many people died and many buildings were and towns were absolutely destroyed from that, as you can see from this particular video that was taken across this structure. So this gives you an idea about what we're talking about when this massive area of land collapsed and what does that look like. So we started looking at the satellite data and the SAR data and saying, okay, we've seen now from that video what's happened. What can we measure, and could we have been able to predict some of this activity that was happening? So what we want to do is start looking at some different locations in the dam. Again, that purple part at the top is where the top of the tailings dam was, and this blue area in front is where the front-facing location was. So we went through and found 3 different areas, these 3 different locations here, P1, P2, P3, and we wanted to take a look at some of the measurements across the data sets to start seeing, okay, what do we see within the SAR data based on these particular locations? Let's look at the mean velocity of those particular locations over time. Again, P1 is where we started showing the tailing deposit area, showing a significant compaction rate that was happening then. So we started looking at the area of P1, so the first location, across a couple different data sets, so we can start going ahead and seeing what does that time series displacement look like. We're looking at data again now from 2015 to 2019, and so we wanted to go ahead and look and see what does that look like. Again, there's that downward slope there showing the displacement in millimeters per year. So at the top of the tailings dam, we're seeing upwards of 200 millimeters displacement. And so that upwards of 200 millimeters over that time of year where that land is sinking. That may not sound like very much when you think about that, but for a structure, that's going to be a catastrophic amount of movement. We looked at another location. This is P2. And this is an area where some of the areas in the body of the dam are showing localized larger displacement rates. So you can see here there's a little bit of a cluster of more of the blue pixels in that particular location. Now we're starting to get into some areas where that compaction and that displacement is not evenly distributed, but in little pockets there. So again, we looked at a couple different data sets. Yes, they were seeing the same sort of trend across multiple data sets, that it's not just isolated to one data set. We want to make sure that we're seeing that across multiple ones so that it's not an anomaly. In this particular location, this is at the front wall of the dam. This displacement was up to about 60 millimeters per year, over those years in that particular location. We then looked at this bottom portion here. This is, again, remember, we see that's where that dam wall first initially collapsed in the video, in location of P3. This is where we start seeing a lot more localized places of the displacement. You can see those clusters of the blue and purple pixels in that particular area. That's where we're starting to see little pockets of more displacement than other locations. At that particular location of P3, the dark blue, that's upwards of 25 millimeters per year for that mean velocity in that particular location. And again, we looked at the rate of that displacement over multiple data sets to make sure we're not looking at anomalies, we're looking at a trend over time within that. And yes, we can see that at that particular location across the years, there was about 40 to 50 millimeters per year displacement at that location as well. So we take a closer look at the entire dam face now, look at the mean velocity. You can see now, looking at the different areas, the compaction at the top, the parts of the wall in the front, and those isolated pockets in the front where we're starting to see uneven balance of that displacement. We still look at the cumulative velocity displacement. So this is all across all the years now. So you can see now in those purple pockets, we're seeing upwards of 60 millimeters per that cumulative area of that displacement. So in these little pockets down the bottom, now we're starting to see some more localized areas where we are able to detect some particular locations there that are having some issues. So that's definitely something that we can see there. So when we take a look across all those areas as well, we picked another location just to see what does that look like in an area that should be more stable. So this new P3 area on the far left in the green location, that's an area of the dam that should be more stable. And that's shown at that top graph, the blue one that looks pretty even. some minor movements and so forth, but overall it's a stable location. Especially when you compare that to the other two lines on there, the green and the red, showing much more rapid rate of displacement in a negative direction. So the interesting thing about this too is, okay, we've done our SAR analysis, we've taken a look at that. What other work was done to show this particular type of analysis? After, again, this was one of the biggest disasters in Brazil's history. So a lot of news agencies were reporting about this too. So the New York Times reported on the sequence of the collapse as the reports were coming out as to how this failure happened, what was happening, and so forth. So the New York Times had an article about, let's take a look at the dam and start looking at where those failure areas occurred as well. So this graphic is from their reporting. You can start recognizing now the dam size, which we should have seen now from the other SAR images, the top of the dam and then the face of it as well. And they looked at these 3 different locations in the boxes shown there as areas to understand where some of those parts started occurring, where some of those failures started occurring initially. That's where they were reporting from their engineers and so forth, doing the analysis and the reports, what had happened after that dam. So we took a look and said, okay, let's match up the SAR data analysis that we've been doing to those 3 locations, and what do we see across those different comparisons. Again, if you look now at those particular locations in the boxes A, B, and C, you can start seeing where that correlates to those more blue pockets of displacement in the SAR data. That's where we can start measuring, again, that displacement was upwards of 25 millimeters per year, and that mean velocity of where those pockets were occurring. Again, the cumulative displacement as well, so this is all the displacement over the years of 2015 to 2019. Now you can see those boxes of where they were showing where those dam failures started and where that corresponds to the purple locations of the highest levels of displacement within the data. So we looked at those time series, again, across the tailings dam, looking at the areas they had picked out in those colored boxes at the bottom, and again, compared to a more stable area, which is that top line in the yellow there. And that's where we can see that that area is fairly stable in that part of the dam. But in those other areas where that collapse occurred, we can see that tracking from 2015 all the way to 2019, you can see that there's that general compaction and much more displacement occurring over time, directly up until the 4 months right before the collapse. So in those 4 months right before the collapse, it's outlined in the blue box right there. You could see that there was even a much greater amount of displacement that was happening right at that point in time. So we could have possibly seen then, if we had been tracking this location, that there's something that needs to be investigated in that particular location there. Again, if we just look at those rates comparing to what the New York Times boxes that they had on their particular report and comparing to the SAR data, you can see that that ongoing deformation showed that acceleration between those years, particularly in those points, in those hot spots where you can see the blue and the purple showing that highest amount of cumulative displacement year over year. And again, right in that particular area, that's where we had an increase in the deformation in the 4 months right before the collapse. And that's the locations right in that front of that dam wall. When we saw the video where that dam failure occurred, that's where that location was, right in the front wall there. So this was a really interesting type of study and analysis to have done. Sadly, yes, it's true that we can actually use Sentinel-1 data, and analysis can be used to monitor these critical infrastructure assets. We could have seen over time, had we been monitoring this, what those changes looked like over time. That data from 2015 to 2019 showed that continuous and significant displacement on the tailings dam, as we're seeing in all the graphs that show the cumulative displacement. Some of those anomalous areas in the body of that dam match the locations where that collapse started, showing acceleration in those last 4 months. We could have seen what was happening in that particular spot. Interesting to note as well, there are 87 mining dams in Brazil that were built like this particular one that failed. Very, very large reservoirs of, again, toxic materials, mine tailings, and so forth. And those walls are just generally built with some walls of sand and silt. So there's many more that are like that we can be monitoring. 27 of those sit directly uphill from cities or towns as well. So that's another reason why it's important for us to be able to look at different types of ways to use remotely sensed data to help monitor critical infrastructure, such as this one here. So thank you very much for your time.